Hey, good morning, everyone. So I was looking at the calendar and I've decided that we can't afford to lose an entire day for an exam. So exam 3, which was supposed to take place, when was that supposed to take place? Supposed to take place on Wednesday, right? That test is now going to be a take-home test that I will send out tomorrow at 1 o'clock. And is that right? Tomorrow? Yeah, tomorrow. Wait a minute, hold on a second. Yeah, okay, I'm sorry, I've lost my mind here. Tomorrow it'll be around 1. It might be a little bit before 1. I'll send that out, and then it's due Friday the 13th at 9 a.m. And then I'll grade those on Friday, and I'll have those grades posted by 4 o'clock. And that's because Friday is the last day to drop a class. So I'm doing that just so everyone has 3 grades to go off of to make that determination. I will send everyone a Dropbox link, and that way you'll know where to send the test. Are there any questions on that? The test will cover everything after exam 2. So mostly like areas between curves, volumes of solids of revolution, volumes of solids with cross sections. Something tells me improper integrals is going to be on there also, right? Because we didn't have those on the last test, or at least we didn't have both types, right? We had type 1, we didn't have type 2. I don't have the test made yet, so I can't tell you exactly, but it will stop at 8.1 sequences. It will not go into 8.2, all right? So there might be something from today that'll be on the test, but you have until Friday to get the test in. One thing I will say, be careful, because with this test, I don't want you to be committing all of your time this week for the test, and you have to still be keeping up with the work that we're going to be doing, our homework. Just stay on top of it, because I don't want you to come back next week and be like, yeah, I didn't do any of the homework for 8.2 or anything like that, because then you're going to just be way behind. All right, so anything before we begin or continue 8.1?
I just had a question about the exam.
Yeah.
So we'll get it tomorrow and have until Friday to complete it?
Yep.
Okay, gotcha. Is there like a specific time on Friday we have to submit it by?
9 a.m.
Gotcha. Thank you, sir.
Yep, 9 a.m. Friday. Any other questions? The test will definitely include all the instructions. If I want you to calculate the entire integral, you can do that. Since you'll be at home and since you have access to computers, I may ask you to do all the integrals to the final answer. So you set up the integral, but then you go to a computer and type in. You don't have to show all the work. You just have to give me a numerical answer. Does that make sense? I just won't require you to show the work for it, right? But let me get the test together and I'll send it out. And if there are any questions on the test, you can always email me or call me or text me or something. Okay, so let's continue where we were last time. We were talking about sequences, and I'd given you a bunch of examples of sequences, and we had stopped talking about factorial, right? That's where we had stopped. This idea of a factorial. And a factorial is just another way of writing a certain type of multiplication. So I gave you the example, something like 5 factorial meant 5 times 4 times 3 times 2 times 1. And in general, n factorial would be equal to whatever the n is. Then you multiply that times 1 less than that, and then 2 less than the n, and then 3 less than the n. And you keep doing that until you get down to 1. Does that notation make sense? N factorial will be n times 1 less than n, then 2 less than n, then 3 less than n, dot, 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 continue, and stop when you get to 1. Yes? Okay. So how about this? Do you agree with this statement? N plus 2 in parentheses factorial would then be n plus 2, and then 1 less than that, so n plus 2 take away 1, then n plus 2 take away 2, then n plus 1, or sorry, n plus 2 take away 3, and then keep doing that until we get to 1. Do you all agree with this? So that's the same as n plus 2. Let's see, when we do that, that's n plus 2 minus 1. That's just n plus 1. The next one is n plus 2 minus 2. That's just n. Then n minus 1. Then n minus 2. And then that would keep going until I get to 1. Does that make sense? But do you agree that all of this together, just in green, just that part, do you all agree that that's just n factorial? Right? N times n minus 1 times n minus 2, that would just be n factorial, wouldn't it? And so this could also be written as n plus 2 times n plus 1 times n factorial. In other words, when you see n plus 2 factorial, you can peel off an n plus 2 and an n plus 1, and then the rest of it would be the n factorial. Now, why is that important? Let me show you. What would n plus 2 factorial divided by n factorial become? So the top, we know, becomes n plus 2 times n plus 1. And then I know that the rest of it is n factorial because we just did that up here, didn't we? Right there. But then I divide that by n factorial, and the n factorials cancel. And so I'm left with just n plus 2 times n plus 1. Does anyone have a question on that? Does it make sense? Okay, let's do another one like that. What would 2n plus 3 factorial over 2n minus 1 factorial be? All right, so I always like to start these by looking at which one of these is bigger. So the bigger one is the 2n plus 3, because 2n plus 3 is bigger than 2n minus 1. So I'm going to start writing out the top, and I'm going to start writing each one out and subtracting 1 each time. So the first factor is 2n plus 3. Then I subtract 1 from that. So if I subtract 1 from that, I get 2n plus 2. And if I subtract 1 from that, I get 2n plus 1. What happens when I subtract 1 from that? Just get what? 2n? Right? 2n. And then if I subtract 1 from that, I get 2n minus 1, right? And then it keeps going, doesn't it? It keeps going. But I'm not going to write the rest of it. What I'm going to say is the rest of it that goes down to 1, right? All of that together should just be 2n minus 1 factorial. And the reason I stopped here is because that's what the denominator is. See, I kept like peeling 1 off, just subtracting 1 each time until I got the expression that's down here. I stopped writing them out. And now this 2n minus 1 factorial cancels with that 2n minus 1 factorial. And I'm left with just all that stuff. 2n plus 3 times 2n plus 2 times 2n plus 1 times 2n, and that's it. If this is difficult for you to see, then I can give you an example with actual numbers, but later on we're not going to be using numbers. So you've got to get to the point where you're comfortable with what I just did there. But if it's easier for you to see this is 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 all over 10 times 9 times 8. I'm not going to do all those times 1. And each of these cancels, right? 10, 10, 9, 9, 8, 8, 7, 7, all the way down. They all cancel. So all you're left with is the 3 out front. That's essentially what's happening. but we're not writing all those out. We're writing that as 10 factorial, and we're leaving the bottom as 10 factorial, and they're canceling. So that's that same thing written out with specific numbers instead of general expressions. Can I clarify that anymore, or are you comfortable with that? Any questions? Okay. All right, so let me just go back. I just want to make sure that I have not talked about what I'm going to talk about now. Yeah, okay. All right, so we need to talk now about convergence and divergence of sequences. And I did not say that, right? I just want to make sure I did not. Yeah. All right, so given a sequence, A sub n, we say A sub n converges if the limit as n goes to infinity of the sequence equals some number L. So guess what? We have to do limits again. All right, we're going to be doing limits again. So we're trying to figure out whether or not a sequence converges. So we have to evaluate a limit. We have to let the n go to infinity and see if we get a number. If the limit does not exist, or is positive or negative infinity, we say A sub n diverges. Some notation. If A sub n converges, we will write A sub n with an arrow pointed to L. So this notation right here means that that limit is true, okay? This is just a notation thing. So let me give you an example. Does A sub n equals -1 to the n over n converge? Does this converge? So what do we have to do to check if it converges or not? Take a limit, right? Let's just do the limit. Let's take the limit as n goes to infinity of this sequence. Now, what does the -1 to the n do to our sequence? What does that create?
Alternating.
And maybe it might be worth it for us to actually write out the first few pieces of this sequence. Let's just plug in, let's plug in 1. What would happen if we plug in 1? We get -1 to the 1 over 1, right? So that would just be -1. What happens if we plug in 2 for n? -1 squared over 2, what would that be? 1/2. If we plug in 3, we get -1 cubed, which is -1 over 3, so we get -1/3. What's the next number?
1/4.
1/4, and so it's just going to keep following this pattern, right? The question is, does this converge? Does it converge or not? So I want to show this to you visually. We didn't really look at sequences, did we? We didn't really look at them visually too much. So this allows me here to graphically show you what a sequence looks like. Okay, so this is the sequence -1 to the n over n. Let me just fix something here. Oh. Okay. So when we plug in 1, right? When we plug in 1, we got -1, right? So when we plug in 1, it spits out -1. When we plug in 2, spits out 1/2, positive 1/2. Then it spits out -1/3, then positive 1/4, -1/5, positive 1/6, and it keeps doing this, right? See that? And let me let it go a little further. Let me go out to 200. Okay. Does that look like it's converging? In other words, as we move out to infinity, does it look like those dots are getting closer and closer to some y value? Okay, so we're looking, remember, we're thinking about the sequence, we're thinking about those numbers that are coming out. These are the outputs, right? What we're looking at here are just the outputs of a function. We know that the inputs are the numbers 1, 2, 3, 4, 5, 6, right? But these are the outputs. So when we're looking at this, we're looking at the outputs of the y values, basically. And so are these y values getting closer and closer to a number? What do you think? Yeah, what number do you think it looks like it's getting closer to?
0.
0, right? It does look like it's getting closer to 0. Now, I would agree with you if you say, well, wait a minute, it's positive and negative, positive, negative. I agree, they are switching positive, negative, but they are getting smaller and smaller and smaller, right? As we continue to go out to the right. Here's what it would look like if we took away the alternating part. If it wasn't alternating, here's what it would look like. Like if we didn't have that -1 to the end, it would just be 1, 1/2, 1/3, 1/4, 1/5. And that, I think that's obvious that that's headed towards 0, isn't it? Okay, but the alternating part doesn't change the fact that it is. It's still headed towards 0. It's just switching back and forth. So how do we show that? How do we show that this limit is going to be 0? So without the picture, here's the way we would have to do this. We would have to just do what we've done in the past with limits. Think about what happens. The bottom heads towards infinity, right? Now the top, is the top headed somewhere? It's switching, right? It keeps switching. 1, -1, 1, -1. So is it headed to one particular number? No, right? It's switching. But would you agree that the top is bounded? This is important. It's bounded. The numerator is always going to be either 1 or -1. It's one or the other, right? So it's a bounded number. It's not going to infinity. It's not headed towards 0. It's stuck between two things, isn't it? And that's what we refer to as bounded. Anytime you have something that's bounded divided by something that's becoming infinite, this will always go to 0. And that's just something you have to know. All right. Is that okay?
Yes, sir.
So what we can say, is that a question, Alex?
No, I was following with you.
Understand. Okay, good. So here's the way I'd write this. This goes to 0. It converges. All right, it converges. All right. Let's try another one. Does this converge? Does this converge? So that means I need to take the limit as n goes to infinity of 2n plus 1 over n plus 3. Now, while you're thinking about that, I'm going to bring up the graph of this while you're considering that. I'll leave it right there. I'm going to actually graph it here. Okay. Y'all ready to look at it? If we plug in 1, we get something. Let me zoom out. I don't know. Okay, there it is. If we plug in 1, we get this, whatever that number is. Oh, it gives us 0.75, 3 over 4. We plug in 2. Oh, shit. May not be able to get this easily. If we plug in 2, we get 1. Okay. Let's see if we plug in 3. There's the dots, right? So let's see what happens here. Looks like it looks like it keeps growing, right? It's getting bigger and bigger. Oh, wait a minute. Hold on. What's going on now? You can't tell that those are dots, but those are dots. Do y'all see that? It's not a solid curve. So as I go further and further and further, does that look like that's growing forever? Or does it look like it's almost asymptotically approaching something? Like it looks to me like that's never going to get up here to 3, right? Maybe it's headed towards 2, right? How would we show that? So anyone have an idea of how we'd show that? If we know that the top is going to infinity and the bottom is going to infinity?
L'Hopital's rule.
L'Hopital's rule, right? That's what we used in the past, but we have a problem. Here's the problem. L'Hopital's rule is what we use whenever we have functions that are doing something like this, infinity over infinity. Because to do L'Hopital's rule, don't you have to take a derivative, right? You have to take a derivative, top and bottom. Well, derivatives means that your functions have to be smooth, because you can't, if you think back about what a derivative is, you go back to Cal 1, the derivative of a function at x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. The only thing you need to know about this is that this limit, you're approaching, because there's no plus or minus here, you're approaching from both sides of a function, and you're trying to find the slope of the tangent line. The problem with a sequence is that if I ever go and I look at a specific x value, like let's say I go into this one right here, I can't do a limit from both sides because there's no curve. It's not a curve. It's not continuous. It's a bunch of dots. So it's impossible for me to talk about the slope of a tangent line at a single point. Does that make sense to you? Sequences are not functions. They're not nice and smooth. Well, they're functions, but they're not continuously smooth functions. So the derivative is off the table. We can't take derivatives of sequences. So we run into an issue. Do y'all see that? We have a problem. But there's a nice workaround. So I put here, L'Hopital. But then I'd say, nope, not continuous, right? Not continuous, so I can't use L'Hopital. So we're stuck, right? We're stuck. But then comes a theorem, okay? Here comes a theorem. A theorem is a mathematical statement that has been shown to be true, all right? And I think once I show you the theorem, you'll agree this makes sense. So let's suppose you're given a sequence A sub n. Consider the function f of n equals A sub n on the real numbers. In other words, instead of looking at it as a function of just integers, go ahead and allow yourself to plug in x. And in fact, let's just look at the function from 1 to infinity. Now, I'll make this make sense after we do a specific example. Here's what the theorem says. If the limit as x goes to infinity of the function goes to L, then so does the sequence. The sequence must also go to L. That's the theorem. Let me show it to you in action. So the example we were just doing, we were trying to figure out whether or not this converged. So we took the limit as n went to infinity of 2n plus 1 over n plus 3. We saw it was infinity over infinity. We tried to use L'Hopital, but then we said, nope, L'Hopital's not on the table. This theorem says, you know what? Don't look at that as a sequence. Look at it as a function of x and replace the n's with x. And then look at that graph just on the interval 1 to infinity. Whatever that graph does, our sequence does. That's what this is saying. Whatever the limit of that function is, that's also the limit of our sequence. So let me show you that back at this picture here. What I'm going to do, I'm going to pull this back so I don't have so many points. What I'm going to do is I'm going to graph the function 2x plus 1 over x plus 3. There's the graph, right? And I'm only going to do it on the interval 1 less than or equal to x less than or equal to, I'll go out to like 300. Oops. So there's the graph, only starting at 1, but allowing it to be real numbers plugged in. So now I have all the little gaps filled in, right? Now this is a function, but see, if the sequence is just points on that function, then whatever the function does, the sequence should do, right? Does that make sense? I mean, it's not like, I don't think this is a big stretch, but what it does is it allows us now to use L'Hopital. We use L'Hopital on the red one, and then whatever we get from that answer, we can say it also applies to the sequence. But we have to understand you can't do L'Hopital on sequences. You can only use them on functions of x. Okay, so now I come here and I say, all right, I'm going to do that. I know that that goes to infinity over infinity. So I'm going to do L'Hopital. So by L'Hopital's rule, the limit as x goes to infinity, I take the derivative of top and bottom, right? So 2 over 1, this is just 2. So the limit is 2, right? Now, whatever that does, this does. So that means that I can draw this conclusion. When you see 3 dots, that's the word therefore. I have not shown that to you, right? I have or I have not?
Yes, you have.
I did, okay. So that therefore what I can conclude is that 2n plus 1 over n plus 3 goes to 2. There's my conclusion. So let me be real clear about this. On your next test, the take-home test, I'm going to ask you to find whether or not a sequence converges or diverges. If you ever use L'Hopital's rule, you better in your work show me that you're converting it from a sequence to a function of x. Then use L'Hopital's rule and then draw your conclusion. Do not use L'Hopital's rule on a sequence. I'll count it wrong. Later in this class, like later meaning next week, okay, maybe even this week, we won't do it. We'll say, okay, we know we can do that. All right, we know we can get it to a function of x and then bring it back. So we will just do L'Hopital's rule, all right, to save ourselves time. But since you're just learning it, I want to really make sure that you understand on this test that in general, you cannot do L'Hopital's rule on sequences, period, end of story. You've got to use the theorem. Okay, you ready for another one? My foot is asleep. Oh my gosh, that hurts.
Sounds painful.
Come on, come back to me. All right, let me give you another example. All right, let's do this one. Say a sub n equals n factorial over n to the n. You know what, can we table that? Let's put that on the back burner. Let's do this one instead. I want to build up to that one. I'm not quite sure we're ready to build up to that one yet. 4 to the n plus 2 over 3 to the n plus 1. Let's do that one. All right, would you all agree that if we take the limit, so I'm asking on both of these, does it converge or diverge, okay? So on this one, we have to do limit n goes to infinity of 4 to the n plus 2 over 3 to the n plus 1. All right, do we all agree that the numerator heads to infinity and the denominator heads to infinity? Yes?
Yes, sir.
Could we turn these into functions of x? Could we turn this into a function of x and use L'Hopital?
I believe so.
Yeah, we could. We could write that as 4 to the x plus 2 over 3 to the x plus 1. We could do that. However, I want you to see something. Do you agree that this is true? That this is just 4 to the n times 4 squared over 3 to the n times 3 to the first. So what I'm doing is I'm using properties of exponents kind of backwards. If you have the same base and you're multiplying, you add the exponents. So this would become 4 to the n plus 2. And then this right here would become 3 to the n plus 1. So I kind of worked backwards. Y'all see that?
Yes, I'm following.
Okay. Now, do you agree that that's equal to this? 4/3 to the n, and then times 16 over 3. So since 4 is being raised to the n and 3 is being raised to the n, I put 4 over 3 raised to the n, and then I just squared that and put it over 3. That's true also, right?
Right.
Now, what do you think happens to this? This right here is a number that's bigger than 1, right?
Mm-hmm.
And you're raising it to a power that's becoming infinitely big. Where do you think that heads?
Just infinity, right?
Yeah, just infinity, right? You have a number bigger than 1 that you keep on multiplying it times itself over and over and over and over and over and over. That should blow up, shouldn't it?
Yeah.
That should blow up.
Eventually,
So this thing should head to infinity. And then times, well, 16 over 3 doesn't change much. So do y'all see that this thing heads to infinity without doing any L'Hopital's rule? Just a little bit of algebraic manipulation, and then understanding that this right here is a number bigger than 1, and so it should blow up when I start raising it to big powers. That good?
Mm-hmm.
Okay, let's do a slight change on that. I'm still not ready for this one up here. Let's table that. I will come back to it. So what about if we did it the other way around? What if we did 3 to the n plus 1 over 4 to the n plus 2? Same thing. Let's try and figure out if this converges or diverges. So I take the limit, n is going to go to infinity. Oh, I forgot to tell you, what is the answer over here? Sorry. Diverges. I forgot to tell you what the final conclusion is. It diverges. It diverges because it goes to infinity. The only way you have convergence is if it goes to a number, right? Infinity is not a number, it's an idea, right? It's a concept. So that's divergence over there. Here, when we rewrite it, I'm going to have 3 to the n times 3 to the 1 over 4 to the n times 4 to the 2. If I do a similar thing, I'm going to get 3/4 to the n times 3 over 16. Now, does the same thing happen? 3/4 is smaller than 1, isn't it? So what happens if you take a number like 3/4 and start raising it to bigger powers? In other words, what happens when you start taking 3/4 times 3/4 times 3/4, bunch of them? Does it get big or does it get small?
It gets small.
It gets smaller. You can check it for yourself, but any number less than 1, you start raising it to more and more powers, the number gets smaller. This is a weird thing. I remember the first time I ever thought about this. I always thought that when you raise numbers to powers, they always get bigger. But that only works if the number is bigger than 1. If the number is smaller than 1, you start raising it to bigger powers, the number gets smaller. So you have to understand that when you do this computation, you let that power get bigger and bigger and bigger. This number actually heads towards 0. And then this number is 3 over 16. So where does this thing go? This limit is 0. Therefore, we have convergence. So this one converges to 0. Do y'all see the difference between these two problems? One of them was convergence, one of them was divergence. And we actually have a formula that says this. It says that if you have a sequence where you have some number r raised to the n, that there's two possibilities. It'll converge to 0 if the absolute value of r is less than 1, and it will diverge if the absolute value of r is greater than 1. What if r is 1? What's 1 raised to any power? 1, right? So we can include 1 here on the top one. But sorry, no, that's not right. It won't converge to 0 though. So we have a third option. The answer will be 1 if r is equal to 1. Now we're not going to see that ever, but that's what would happen. If this base is 1, then it doesn't matter what power you raise it to. It's just going to stay 1. So what I'm saying is up in this problem right here where we had that 4/3, that 4/3 was bigger than 1, and that's why we diverged. And then over here in this one, our 3/4 was actually smaller than 1, and that's why we converged. Do y'all see the difference between those two? Okay,
Yes,
now let's do another one. We'll do one more before we do that one that I put on the back burner here. How about this one? A sub n is equal to arctangent of n over n squared. This one is only interesting because of what's happening on the top. So let's see, if we take the limit as n goes to infinity of arctangent of n over n squared, I think it's clear that the bottom is headed towards infinity. The question is, what is the top headed towards? So what is arctangent of positive infinity? We've dealt with this with improper integrals. Imagine what the arctangent would be doing as you headed towards negative infinity. Isn't that going to do what the tangent, inverse tangent function does? Does anyone remember what that answer would be then?
Would it be approaching 0? Oh, it just
No. This is the tangent function, right? That's tangent of x. As you get closer to pi over 2, right? As you approach pi over 2, the function takes off to positive infinity. So the inverse tangent, right? The inverse tangent of infinity should spit back the pi over 2. Y'all remember doing this with improper integrals,
Oh, yeah, I think I know.
right?
I'm sorry.
We did talk about this in improper integrals. It did show up a few times. So what should happen to this sequence then? If the top is headed to pi over 2 and the bottom is headed to infinity. Pi over 2 is just a fixed number, isn't it?
Right.
So any fixed number divided by a number that gets bigger and bigger and bigger should head towards 0.
Hmm.
So this sequence converges to 0.
Convergence.
Converges, yeah. All right, let's take a look now at this one.
And that'll be any number over infinity.
That's
is
right.
0. Okay.
That's right. Well, what I like to tell my students in Cal 1 is that if you take a limit and you get a fixed number over something that's going to infinity, that will always go to 0. In fact, I tell them that not only can it be fixed, if you just have a bounded on top over infinity, that goes to 0. Any of those two situations. Now this, remember, is in the limit. When you're taking a limit, if that happens, you know the limit 0.
All right.
I'm going to give you a second to look at that next one. I just want you to consider what's happening here and then maybe what we can do. I don't anticipate anyone's going to get it, but I want you to think about what problems you're going to run into trying to approach it the way we've been approaching it. All right, so this thing is headed, where's the top headed? Think about if this was a huge number. A billion infinity, right? That'd be a billion times a billion minus 1 times a billion minus 2. It's gonna be a huge number, isn't it? And the
Right.
bigger n gets, the bigger that gets. So that should head to infinity, shouldn't it?
Right.
And then the bottom is a number that's becoming infinite raised to something that's becoming infinite. That's also a huge number. That's headed towards infinity. So we have infinity over infinity, right?
Right.
So at this point, you might be thinking L'Hopital. Okay, you might be thinking L'Hopital. But to do L'Hopital, you'd have to switch that over to a function of x. And does anybody know why we can't do this?
Because of the factorial?
Yeah, factorial is only defined for integers, for non-negative integers. So when it comes to factorial, we know that we can define one, well, we can say, well, 1 factorial is 1, 2 factorial would be 2 times 1, which is 2. We can do 3 factorial, which is 3 times 2 times 1, which is 6. And we could keep doing this, right, for all these counting numbers. But the inputs, right, are only 1, 2, 3, 4. In fact, we can actually do 0 factorial. Does anyone know what 0 factorial is?
Just 0, no?
It's not 0. It seems like it would be 0, right? It's actually
Right.
1. And I'm going to highlight this because we actually define it this way. Anytime we define something in math, we usually put a colon in front of the equal sign. We define 0 factorial to be 1. And I know that that seems very strange, but we need to know this for the rest of the class. 0 factorial is 1. Now, if you do not like that, which most students don't like that because it's like, what? How can 0 factorial be 1? You have to understand that this factorial that we're dealing with here is actually defined a different way when you get higher in math. And when you get to that point, you realize that 0 factorial makes perfect sense and that the answer being 1 makes perfect sense. But right now, you're just going to have to accept it on faith that 0 factorial is 1, right? You're just going to have to accept that. I apologize, but that's the way it is, all right?
Yeah.
Yeah, I'm just going to leave it at that. But right now, we don't have a way of doing this because that's supposed to be defined for all numbers between 1 and infinity. So right now, if I asked you what's 1/2 factorial, well, it doesn't work because we don't know what 1/2 factorial is because we've only made sense out of it for the nice counting numbers. All right. So we cannot. And then, even if we could, what's the derivative? What's the derivative of x factorial, right? I mean, who knows, right? Let's try let's just go to Desmos. If I put in here n factorial on top, divided by n raised to the n, let's see what it does. And I'm going to take this one out of here. See if we can see this. Here's the sequence, okay? Let's start looking at it. Whoa, that looks like it converges, doesn't it? To 0? That looks like that converged very fast too. It was like, boom, just right away, it just dropped. So it looks like we have convergence. Now let me try and have the computer do that as a function. If I do x factorial divided by x to the x. Oh, it did it. Wow. I'm impressed. This Desmos is really pretty awesome, actually. Most graphing calculators wouldn't do that. So it looks like that it's defining the factorial, isn't it? It didn't define it for negatives, which makes me a little concerned, but it's okay. All right, well, that didn't show what I was trying to say. You don't know what the derivative of x factorial is, and we're not going to get into it. So we can't use L'Hopital, all right? We cannot. So this example is an example where I need to show you how to do this so that you see it, and then you're like, oh, okay. Yeah, I wouldn't have thought of that, but so here's what I'm going to do. I'm going to use what's called the Squeeze Theorem, and this is something that you should have talked about in Cal 1, the Squeeze Theorem. And the idea behind the Squeeze Theorem is this. We're going to look at our sequence, A sub n, and we're going to try and see if we can't come up with two new sequences, B sub n and C sub n. One of the sequences is going to be smaller than our A sub n, and the other sequence is going to be bigger than our A sub n all the time, okay, so that that inequality is true. Then after we do that, we're going to take the limit of this sequence, and we're going to show that that goes to some number L. And then we're going to take the limit of this sequence and show that that also goes to L. So if this sequence goes to L and this sequence goes to L, then what does this sequence have to go to? L, because it has to be between, right? That's the idea of a squeeze theorem. You try and squeeze the sequence you're looking at between two other sequences that you know where they go. All right? The challenge for us is to create the squeeze on that sequence. We have to create the two sequences that are bigger and smaller than it. So I'm going to do that right here. N factorial over n to the n. So here's what I want you to consider. N factorial on top is n times n minus 1 times n minus 2 times n minus 3, and it keeps going down till I get to 1. And then on the bottom, what does n to the n mean? N times, n times, n times, n, right? Just repeat it. N times, n times, n times, n times, and I'll stop at the very last one will be an n. And there should be n of these n's, right? There's n of these. And so what this creates is a nice little kind of set of columns. Every one of those pieces is over an n. Do y'all see that? Okay. So all I've done is rewritten what the original problem was. Now this. Would you agree that this is definitely bigger than or equal to 0? Because the numerator, these are all positive numbers, and the denominator is all positive numbers. So that's always true, yes?
Yes, sir.
Okay, now this is the hard part. I'm going to try and show you that this is smaller than something. So let's see if you can agree with this. This first one's easy. Do y'all agree that that's equal to 1? Right?
Yes.
Okay, so I could say that that's less than 1 times, now this one right here, do you agree that n minus 1 divided by n, do you agree that that number is a little bit smaller than 1? Whatever that number is, it's smaller than 1. So if I put that here, well, I know, let me think of a number. If this number right here is smaller than 1, then if I put a 1 here, do you all agree that that would be bigger? Like this piece right here is bigger than that one, right? Like that 1 is bigger than that.
Right.
Okay, now the next ratio we have here, that's also smaller than 1. So if I put a 1 over here, that 1 would definitely be bigger than that one. And couldn't I keep doing this for each one of these? Right?
Should be able to.
Okay, so if I did it for each one of them, the very last one would be 1, right? Wouldn't it? But there's a problem, because what is the right-hand side equal to? 1, right? So we're saying that this thing is between 0 and 1. Great, it's between 0 and 1. That doesn't create the squeeze we need. We need a squeeze. So watch what I'm going to do. Instead of looking at this very last one as being a number that's smaller than 1, I'm actually going to just have you think about it this way. It is just 1 over n, right? So what if I instead replace this last one with 1 over n? Do you agree that the 1 over n would be bigger than or equal to 1 over n here? So all I'm trying to get you to see here is that everything in blue is definitely smaller than 1 times 1 times 1 times 1 times 1 until I get to here. But then the part in yellow is the same, which means that all of this on the right-hand side should be bigger than all of this. And now I have something I can squeeze, because if I take this and I take the limit as n goes to infinity of 0, well, where's that going to go? It's always 0, isn't it? Right? It's just always 0. And then if I take this one over here and I take the limit as n goes to infinity of all of that, but that's just 1 over n. Is it obvious that that goes to 0? As n goes to infinity, a fixed number over infinity goes to 0. So if this right side, which always has to be bigger than this, and this left side, which always has to be smaller than this, if these both go to 0, and that's the key, then do you agree that the one in the middle, when I take the limit of it, wants to also go to 0? It's been squeezed, right?
Right.
And that's how you show that. I'll give you another example. Okay, so you can see another example of this. I'll just stay here for another second in case someone needs to write something down. Any questions while I'm waiting?
No.
Okay, here's another one. Let's make that n factorial inside. That way you can't use L'Hopital's rule. All right, so if we think about what's happening here, well, let's take a look. Sine of n factorial over n squared. There it is. And I'll put here, no, I'm not going to do that, but look at this. We know that the sine function is always going to, the sine function, no matter what you ever plug into it, will always be between -1 and 1. Do y'all agree with that?
Yes.
Let me do it this way. Let me take the n squared out of here. Let me just put 1 down there. Here's what that's pretty awesome looking. This is what sine of n factorial looks like.
Is that?
It's just all over the place, right? It's all over the place. Now, because this computer is smart enough, I'm going to put x factorial in here. Oh, oops, that's too much. Whoa, it's having, yeah, no, I better get rid of
Is
that.
it just crashing?
It didn't crash, but it was like, it was so thick, like the curve was so like oscillating so much that it just looked like a solid block. Okay, so there it is, right? That's sine of n factorial. It's almost like a weird scatter plot, right?
Or random, yeah.
Yeah, it's very random looking. It's not an alternating sequence. It's not positive then negative, positive then negative, positive then negative. Sometimes it stays positive. Like here it's positive, right? When I plug in 1. When I plug in 2, back up. When I plug in 2, come on. I'm still positive, right? I'm going to plug in 3. Now I'm negative 4. I can't do it. 4, whatever. You see it, right? Wow, it's just
Yeah.
kind of all over the place. So it's not an alternating sequence. It is switching signs, but it's not something that's just every single time. So, and then we divide it by n squared. And now it's like, it's still kind of randomish, but do you see that it looks like it's approaching 0? So let's just show that. So the way I'm going to do this is as follows. I need to somehow, I'm going to use Squeeze Theorem. I need to somehow get control over this and put it between 2 things. The way I'm going to do that is going to be a little weird though. I'm going to start with what the numerator is. And the reason I'm just starting with the numerator is because I know a lot about sine. The sine function is always bounded between -1 and 1, right? No matter what you ever plug into sine, I can say for sure it's between these 2. Yes? Then to get it to look like the original function, I'm just going to divide everything by n squared. So that is a legal move. I can divide everything by n squared, and this inequality should still hold. Now I have what I'm looking at in the middle, and it's squeezed, right? It's between 2 things. I just need to hope that both of these, when I take the limit, that these both go to the same place. Do they? If I take the limit as n goes to infinity of -1 over n squared, is that the same as the limit as n goes to infinity of 1 over n squared? What do those both go to? 0, right?
Oh, 0.
They both go to 0 because it's a fixed number over something that becomes
Oh,
infinite.
that's right. Yeah.
So that means this guy's got to go to 0 too. So this converges to 0. All right, we have one more. We have one more, and then we're not done with this section. We still have more in this section, but we have one more, and then we're going to switch gears to a different kind of topic. Any questions?
No.
I like this last one. I'm going to give you a sequence, all right? I want to know if it converges or diverges. Okay, does this converge or does it diverge? But I'm not going to give you the formula. I'm going to give you the sequence actually written out. The first term in the sequence is the square root of 5. Then the next one is the square root of 5 times the square root of 5. Then the next one is the square root of 5 times the square root of 5 times the square root of 5. And the next one is the square root of 5 times the square root of 5 times the square root of 5 times the square root of 5. I think I got that right. Yeah. Dot, dot, dot. Does this sequence converge or diverge? This should bother you a little bit. It would be much nicer if I had the formula, right? Because then I could just take the limit and let n go to infinity, right? So I think we should try and get the formula.
Okay.
So one thing we could do is get rid of the radical notation and use rational exponents instead. So I could rewrite that first one as 5 to the half, right? That's what square root of 5 is. Now this second one, how could I rewrite that? I could do, see, the whole thing is to the half, right? And inside it's 5 times 5 to the half. Right, so this piece in here is that arrow, but then the whole thing is being raised to the 1/2 again because it's another square root. Does that make sense?
Yes.
Okay, now inside this 5 times 5 to the half, I really look at that as being 5 to the first power times 5 to the half power. You add the exponents. 1 plus a half is 3/2, right? To the half. And when you have something to a power, what do you do to those powers?
Multiply.
Multiply, right? So 3/2 times 1/2, that's 5 to the 3/4. Y'all agree?
Yes, sir.
Okay. Let me look at the next one. The next one, again, I have the square root, so something to the half. I have this 5, but then times, now do you recognize this in yellow? Do you recognize what that is?
5 to the 3/4.
Yeah, this is the one before it, isn't it? It's that one, which we already said was 5 to the 3/4. Right? So that's just going to be 5 times 5 to the 3/4. And now, again, we need to take 1 and add 3/4. What's 1 plus 3/4?
7/4.
7/4. And then we're going to do that to the half power. So now we multiply those powers, right? If we multiply those powers, we get 5 to the 7/8. And we go again. The next one is going to be something to the 1/2. We have this 5 that comes down, times, and now in blue, you see that? You recognize that? The previous one, isn't it?
Yes, sir.
Which was 5 to the 7/8. We're starting to create a pattern here. This will be 5. Let's see, we have to add 1 plus 7/8. That should give us what? 15/8. And then to the half. And then when we multiply, we should get 5 to the 15/16. Can anybody predict what the next one will be? Try and see the pattern here.
31 over 32.
31 over 32. So what are you seeing as the pattern?
Times 2 to the top plus 1, and then times 2 on the bottom of the
Okay,
exponent.
so you're just doubling, you're going to double the bottom each time, right? And then take 1 away on the top. So the next one will be 64 on the bottom, and then 1 less than that is 63 on the top. Right? So can you come up with a formula then? Well, we know that the 5 is always here, right? 5. Now, what about the numerator? I mean, sorry, not numerator. What about the exponent up there? The bottom, the denominators are always what? 2, 4, 8, 16, 32, 64. We recognize those as powers of 2, right? Powers of 2. So this fraction here, I should have 2 to the n on the bottom, right? So that when you plug in 1, you get 2. That's this one. When you plug in 2, you get 4. When you plug in 3, you get 8. 4, you get 16, right? And then the top is just that 2 to the n. It's the same number, but you have to take 1 away from it, don't you? I don't like the way I wrote that. 5 to the 2n minus 1 over 2 to the n. I said 2n, 2 to the n minus 1, 2 to the over 2 to the n. That's our sequence. We got a formula for it, right? Now we take the limit as n goes to infinity. How are we going to figure out that limit? The only part we have to really figure out is what's happening here, right? What's happening there? So how about I do this? How about I rewrite this slightly different way? How about we rewrite that as 2 to the n over 2 to the n minus 1 over 2 to the n. So what I did is because I had a single expression denominator and 2 terms on top, I split it into 2, like this. And this is really just a 1. So can you tell me now what happens if n goes to infinity? The only thing that's impacted is this piece here, right, in blue? What does that go to as n goes to infinity?
0.
0. So at the end of this all, you just get 5 raised to the 1 minus 0, which is just 5 to the 1, which is just 5. The sequence converges to 5. So if you were to get on your calculator and do square root of 5, and then take that answer, multiply it by 5, and take the square root again, and then take that answer, multiply by 5, take the square root again, and then take that answer, multiply by 5, square root again, your numbers would start marching closer and closer to 5. If you don't believe it, here I'll put the sequence right here. 5 raised to the 2 raised to the n minus 1 over 2 raised to the n. There we go. Pull this back. Where is it? There it is. Here it comes. Right? It went pretty quick there, didn't it? It converged pretty quickly. It was like boom, 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 then shoop, converged to 5. That problem was just to show you how you can mess with exponents and come up with a formula. That's what it was more about. The actual like figuring out the limit part, this part wasn't actually that bad. This right here, pretty simple algebra here, but it was all this right here, not necessarily a natural process. Okay. Still in 8.1. Make sure I've covered the things I wanted to cover here. So look, when you get to your homework on this part of the section, the problems up through number 30, you're going to be relying on all sorts of things from calculus 1 in terms of limits. You know, sometimes you'll be using L'Hopital's rule, sometimes you'll be using Squeeze theorem. It's just going to depend on the problem. So you need to make sure you go through those, because there's no way that I can do enough examples here today to give you a full flavor of everything. So make sure you work through the homework problems. Now we're going to move on to some definitions. So we're still in this section, but we need to have some definitions so that I can give you this really nice theorem that we're going to use at the end. Okay. So the first definition is this: a sub n, so let's say we have a sequence, is said to be increasing if a sub n is less than or equal to a sub n plus 1. For all n. So what this means is this. It means when you look at your sequence, the first number in your sequence is smaller than the, or equal, strictly increasing. Sorry, that's not less than or equal to, that's just strictly less than. The first one is smaller than the second one, which is smaller than the third one, which is smaller than the fourth one, and that continues forever. And that means if you look at these, you know, graphically, they keep getting bigger and bigger each time you move to the next one. Does that make sense? It's like an increasing function, like a derivative that's positive. From left to right, the sequence should be going up. Okay, that's what increasing is. Decreasing is the opposite, right? So a sub n is decreasing if a sub n is bigger than a sub n plus 1 for all n. that would mean that the first one is bigger than the second one, which is bigger than the third one, which is bigger than the fourth one, and so on and so forth. So graphically, the sequence should be going, down as you move from left to right. Those two definitions are pretty intuitive. Most people understand that. Yes, does that make sense? Going up, going down? Okay. So those are your first two definitions, increasing sequences and decreasing sequences. Now the third definition is related to those two. In either case, A sub n is called monotonic. Monotonic. Now, students will ask me, if somebody gives you a sequence, does it have to be increasing or have to be decreasing? And the answer is no. You can have a sequence that's neither increasing nor decreasing. Like the one I did earlier, that one that was sine of, let's just do sine of n. There, sine of n. There's an example of a sequence that is neither increasing nor decreasing. It's all over the place, isn't it? So you don't have to be increasing, you don't have to be decreasing, but if you are always going up, then that's called increasing. If you're always going down, then it's decreasing. This would be an example of a decreasing sequence. This would be an example of an increasing sequence. That goes up really fast. Okay, that's always going up. Yeah, that's okay. I'll just leave it. Okay, so you don't have to be one or the other, okay? But if you're one or the other, if you are one of these, doesn't matter which one it is, in either case, you're called monotonic. The sequence is called monotonic. So if I tell you, hey, I've got this sequence and it's monotonic, I'm not telling you that it's increasing. I'm not telling you that it's decreasing. I'm telling you it's one of them. Not telling you which one, I'm just telling you it is one or the other, okay? That's monotonic. Any questions on that? Okay, the next set of definitions has to do with what we call bounded sequences. So more definitions here. A sub n is called bounded above it's bounded above if there exists a capital M, which is a number, okay, such that A sub n is less than or equal to capital M for all n. So I like to think of this idea as saying that our sequence has a ceiling to it. There's a roof that it never crosses. That's what it means to be bounded above. So I'm going to go back. I'm going to go back and look at a graph here. I'll bring this back up in a second. I don't know why my M's look so weird, but I'm going to put that sine of n in here again. That was a really cool looking sequence. Okay, let's talk about this. Is this sequence bounded above? So can you find an M such that that M is always bigger than everything in your sequence? So I'm going to, oh, I didn't mean to do that. So what about this? 1.5. M equals 1.5. Would you agree that I have found a number that my sequence is always below it, right? Now, is that the only M? No, there's any number that you could find that is going to be above this would be an example of an M. So for a sequence to be bounded, you just have to find one M. It doesn't matter what it is, one M that is always above your sequence. And what do you think's coming next? We just talked about bounded above, right? A sub n is called bounded below. If there exists a, let's say, little m, such that our sequence is always bigger or equal to that little m for all n. So it's the same thing, but the other way around. Now we have a floor to our function, or to our sequence, something that's always smaller than it. I'll go back to those. I'll leave those up for a second. But here, we obviously have a floor, right? For this one, you could use negative 1.5. Anything here, right, would work. Okay. So this is an example of a sequence. This one right here is an example of a sequence that's both bounded above and below, isn't it? Bounded above and below. So if you have that case, if A sub n is bounded above and below, we say A sub n is bounded. That would be our last kind of definition here. So this is a little bit different than the increasing and decreasing. Think about what I said about increasing and decreasing. A sequence is increasing if it's going up from left to right. A sequence is decreasing if it's going down left to right. In either case, it's called monotonic. Here we have bounded above, which means we have a ceiling. Bounded below means we have a floor. In order to be bounded, you have to be both bounded above and below. You have to have a floor and a ceiling in order to call a sequence bounded. Any questions? Okay, so let's do an example.
Wait, sorry, Professor. I had one question.
Yep.
So it's still a ceiling if it's on like the top of the function, or a floor if it's like below. Like both. Okay, so if it equals, like if there are points along the ceiling, that can't be a thing, right?
Yeah, so if your sequence touches your ceiling, that's okay. It just can't go past it.
Okay, gotcha.
Yeah.
Thank you, sir.
Mm-hmm. Yeah, so let me go back. I'll show you this one again. Here, this right here, this sign n, we could say that the ceiling, a ceiling, not the only ceiling, we could say that a ceiling here would be, oh, sorry, that was supposed to not go down. M equals 1 would be a ceiling. That would be an upper bound because the sequence always stays either equal to it or below it. And then you could say the floor here, -1 would be fine also, because the sequence never goes below -1. It's okay that it touches, okay? But keep in mind, I could have used a different number, like 1.3 would also be a ceiling. This is not saying we have to find the ceiling that is closest to the sequence. Anything above is a ceiling, anything below is a floor.
And we don't worry about the sides, right?
That's right, you don't, because we're only looking at the outputs, and we're basically trying to make sure that our outputs are stuck between two numbers, right?
Okay.
Our outputs are always between two. The left and right, we know that this left is never going to go anywhere to the left of this, because remember, we're going to be plugging in 1 and then 2. And then to the right, we know we're going to infinity. So we know that the sequence just keeps going out to the right forever. So we're only looking at the y value, so to speak. All right. Let's do an example. Show a sub n equals 1 minus 3 over n is monotonic. And then show A sub n is bounded. All right, so look, we are now getting into this new realm that you're going to have to become familiar with or comfortable with in a relatively short amount of time, where we're being asked a question where we're not going to do some computation like integration or oh, it's a volume of solid, so we're going to use this formula. This is all up here now. This is all, you have to show this is true. Like you have to show with whatever you write, you have to convince whoever's looking at your work first that this is a monotonic sequence, and second that it's bounded. So that means you have to know what you need to show in order to do that. So this is the first time that I guess we're starting to get into what really like pure math people have to do, and that is communicate something across to somebody else following logical steps. Okay, so I'm going to start with monotonic. So I need to show it's monotonic. So I'm going to write that down. I want to show, I like to write WTS. I want to show, that means want to show that A sub n is monotonic. What does that mean I need to show? That implies that A sub n is either increasing, right, or decreasing. I need to show that it's one of those two, right? To show that it's monotonic means that I need to show that it's increasing or decreasing. How do I know that? Because that's the definition of monotonic. Monotonic means in either case, it's monotonic. Okay, so that means it's either increasing or decreasing, which means that's what I need to show. It's one or the other. So how do you think we're going to figure out whether or not the sequence is increasing or decreasing? I mean, we have to pick which one we're going to try and show. It's one or the other. Which one is it? How do you think I could get a better grasp as to which one it is?
Use a limit.
Use a limit. Okay, so a limit would tell us where it's going, right? That would tell us where it's going out in infinity, right? So let's say it goes to 0. Let's just say, does that tell us whether or not it's going up towards 0 or down towards 0? No. So why don't we just start writing out a few of these? Okay, let's just start like plugging numbers in and let's see what happens. So let's write the sequence out. It might help us. So we plug in 1, what do we get? Plug in 1, you get 1 minus 3, that's -2. What happens if you plug in 2? 1 minus 3 halves, I'll figure out what that is in a minute. 1 minus, what happens if we plug in 3? 1 minus 1. What happens if we plug in 4? 1 minus 3/4. Are y'all with me? 1 minus what?
3/5.
3/5. 1 minus 3/6. 1 minus 3/7. Okay, so let's see if we can't figure out what this is. Let's clean it up. 2 minus, let's see, that's -1/2. That's 0. That's 1/4. That's 2/5. That's 1/2. That's 4/7. So I'm just doing those computations in my head, but I'm assuming you could get those too, right? What does that look like it's doing? -2, -1/2, 0, 1/4. What are those numbers doing?
It's increasing.
Increasing. So it looks like I need to show it's increasing, right? So I want to show it's increasing. What does it mean to be increasing? So I want to show that A sub n is smaller than or equal, no, strictly smaller than A sub n plus 1. Isn't that what it means to be increasing? Look back at the definition. To be increasing means that A sub n has to be less than the one before it, right? I'm sorry, A sub n has to be less than the one after it, not before it. So the one that's here needs to be smaller than the one next to it. Do y'all agree? Now I can look at these and I can see that they are, right? I can see that this is smaller than this is smaller than this. When we say smaller, we mean on a number line further to the left. But just because the first few are smaller and getting bigger does not mean it holds the whole way down. So you have to show this algebraically. And what I mean by that is this. You have to rewrite what is a sub n? 1 minus 3 over n. You want to show that that's less than 1 minus 3 over n plus 1. So the nth number in this sequence is just replacing the n with n. The n plus 1 number in the sequence is replacing the n in this formula with n plus 1. I need to show this is true. You need to show that this is true. Show it, right? We have to show that's true. So this is almost to us like a question mark. We don't know if it's true, but if we can prove that that inequality is true, we will be done. Does that make sense? Okay, so now the rest of this is just algebra. I'm going to subtract 1 from both sides. So now I have this, -3 over n less than -3 over n plus 1. Okay, I think at that point we could say that this is true, but here's what I'm going to do. I'm going to multiply both sides by -1. What happens when you multiply an inequality by a negative number? On both sides of an inequality, what happens to the inequality sign if you multiply or divide by a negative?
The sign switches.
Sign flips. So this becomes 3 over n greater than 3 over n plus 1. See how the inequality flipped? Because I multiply both sides by -1. Now I'm going to cross multiply. So I get 3 times n plus 1 is greater than 3 times n. I'm going to distribute the n on the left, or the 3 on the left. And then finally, I'm going to subtract 3n on both sides. And what I get is a final statement, 3 is bigger than 0. And do we agree that that's true? We all agree 3 is bigger than 0? So we put a check, which means that we have shown this is true. See, we said, okay, we think it's increasing. So this is what we need to show. We replace these with the actual sequence itself with n here and then n plus 1. And then we work the inequality out until we get to a final result that is a true statement we all agree on. If this would have said 3 is less than 0, then that means it's not increasing, okay? That means you better go look at it being decreasing then or something. But this is the work. This is the work I need to show in order to convince somebody that it's an increasing function or increasing sequence. Is that okay? So therefore, a sub n is increasing. What is the next thing I need to show? I showed that it's monotonic, right? Because it's monotonic increasing. I need to show it's bounded now. New page. I want to show a sub n is bounded, which means I need to show two things, don't I? I need to show one, I want to show a sub n is bounded above. And then I want to show that a sub n, a sub n is bounded below. So let me try and show bounded above. I look back at the sequence that we wrote out. -2, -1/2, 0, 1/4, right? Can you all think of a number? Yes.
On the new page you made, you accidentally wrote as 1 minus 1 over n. It's 3 over n. Just a.
Oh, yeah, no, thank you. Thank you. Thank you. It is 3. Yeah, 3 over. I think 1 over n was the example I gave on Thursday to my other class. All right, so I want to show it's bounded above, right? So I go back and I look at the first few pieces here. Just by looking at these, what do y'all think? What is a number that it looks like these are never going to get bigger than?
1.
1.
1, maybe 1, right? Why don't we be safe and just go with 2? Like, it looks like maybe these are getting closer to 1, but you know, if 2 is always bigger, then that would be enough, right, to show it's bounded above. You could pick 10, okay? Just don't pick 1/2, because look, 1/2's here, and this number's bigger than 1/2. So we're gonna go with 2. Here we go, I'm gonna show it. Let capital M be equal to 2. See, in order to show something's bounded, I have to show that there exists a number that's always bigger than the sequence, right? So there it is, I'm letting that number be 2. Now I check, is a sub n always less than or equal to capital M? Is that true or not? Well, let's write it down. Is 1 minus 3 over n always less than or equal to 2? Question, is that true? Let's do some algebra again. How about we subtract 1 on both sides? Why did I not flip the sign over, the inequality? Why did I not do that?
You didn't multiply by negative.
Yeah, I didn't multiply by negative, I subtracted on both sides. You don't flip when it's subtraction. All right, at this point, am I done at this point? Is that inequality enough for you to be like, okay, yeah, that's true? Yes or no? Somebody who thinks yes, just tell me why you at this point would be happy to just put a check mark and be like, yep, that's good.
Because -3 over n is negative, and then 1's positive.
Yeah, so look, remember, what are we plugging in for n here? N is either gonna be 1 or 2 or 3 or 4 or 5 or 6, right? So you can guarantee me that 3 over n, that's always a positive number. And then you put a negative in front of it, so that's always gonna be a negative number. So the left side of this is negative, would you all agree? Isn't a negative always smaller than or equal to 1? Yeah, that's true, right? Now, if you don't like that and you wanted to continue to work on this, you could start manipulating this more. Like you could have just said, okay, I'm gonna take that and let me write it down here. Maybe you would do this. Maybe you would multiply both sides by n. Is that true? Is n always bigger than or equal to -3? Yeah, because remember, we're a sequence, right? The sequence has a domain restriction. The domain restriction is you can only plug in 1 or 2 or 3 or 4 or 5 n for n, right? So this would be true. The thing is, you have to show it. Do not give me this step right here and just be like, yep, that's true. No, you have to show a little bit of work to convince me. All right, we're not done. Now we want to do this. Let n, oh, sorry, we want to show it's bounded below. Sorry. So go back and look at the sequence. Bounded below. Does it look like there's a number that's always going to be smaller than all these?
-3.
-3.
-3, yeah. Could we use -10? Sure. Could we use -5? Sure. But someone said -3. Let's go with that. So let's let little m be equal to -3. And now I have to ask myself this question. Is a sub n always bigger than or equal to little m? In other words, is 1 minus 3 over n always bigger than or equal to -3? More algebra. Watch this. Somebody tell me what I did here. How did I get from here to here?
Just multiplied by -1.
You added 3 and then added 3 to the end of the other side.
Yeah, I took the -3 up this side by adding it on both sides, and that became the 4. And then I took the -3 over n and added it on both sides, and that's what made it positive on the right. Look, you can use any algebra you want, as long as you're not breaking any rules, okay? So we all might do this a little different. Next thing I'm gonna do is I'm gonna multiply both sides by n. At that point, I could probably stop. But I'm going to go one more step and I'm going to divide by 4. Now, is that true? Is n bigger than 3/4?
Well, you multiplied by n and didn't switch the signs.
It did not flip it because you only flip the sign if you multiply by a negative number. And I know that n's not negative because n can only be 1, 2, 3, 4, 5, 6. So we are relying heavily on all of the work that we're doing here. We are relying heavily on the fact that n can only come from this list of numbers. So when we multiply by n, no need to worry about flipping.
Since n is always a positive integer, it'd prove that it's greater than 3/4.
That's right. And so we can say, yep, that's true. Okay, now, why in the world is this useful? Here's why it's useful. We only have 2 minutes left. We have the last theorem. And here's what the theorem says. Every monotonic bounded sequence blank. What do you think? Every monotonic bounded sequence does what?
Converges?
Converges. Think about it. Let's say you have a sequence, right? Let's say that it has a ceiling, capital M. Let's say that it has a floor, little m. And let's say it's monotonic. So you get to pick increasing or decreasing. What do you want?
Increasing.
Increase. Okay, so here I go. I'm gonna start trying to draw it. Doesn't matter where I start. I have to start between these two. There's my first one. Now, my next one has to be above that one, right? My next one has to be above that one. Maybe it's way above, maybe barely above, but what happens? Oh, now my ceiling is there, right? So what happens is you eventually have to flatten out. You have to. Now, you can't come back down. Why can't I come back down? Because then you're not increasing anymore, right? You have to be increasing. So you can't do that. So you have to be you have to be converging now. That sequence must converge. So what we're going to see later on in this class is that later, we're not going to be so concerned about what things converge to. It's going to be very difficult, in fact, for us to figure out what things are converging to. We're just going to be wondering, does it converge or not? And you might be like, well, that's no good because then we can't get an answer. But trust me, it's all about convergence or divergence later. If you don't believe me, you can look at your formula sheets and you can see on this series test sheet, look what it says. Summary of convergence and divergence tests. All we're going to be doing is trying to see if something converges or diverges. That's all we're going to be doing. And these are a list of tests that we have to run to figure out whether or not, we haven't even talked about series, but I'm just trying to point out to you that the convergence and divergence is what becomes important later. Okay, that finishes 8.1. Okay, we are done with 8.1. You should do all the homework in there that's been assigned and then be ready on tomorrow for that test to come to you, right? Are there any questions? This reminds me of this story. Y'all can leave if you need to leave. I know I'm not going to hold you, but this reminds me when I first started teaching, I had a colleague of mine who, well, we shared an office together, and he was really kind of I didn't like him at all. He was very arrogant, and he was very, I don't know, I'll turn off my video. Yeah.